Good morning and welcome to our very first live stream class session of our semester in pre-calculus. I'm Dr. Salamone, for those of you who haven't yet met me. Let me lay out a little bit about what our agenda is over the course of the next hour or so. We have a very short, fast-paced semester this semester. We're doing pre-calculus in 5 weeks. So what that means is that we've got kind of a lot of ground to cover, not a lot of time to cover that ground in. So what I'm hoping to do is do a couple of these live streaming sessions per week over the course of the 5 weeks that we'll be together. And what I really want for each of these sessions is I want it to be responsive to the questions and the sticking points that you all have as you're working through this material. So what I'm going to want to do as the semester goes along is use your questions, use the results from your group conversations, and all the ways that we interact as things come up in our discussions over Slack over the course of the semester. I want to be able to use those to kind of seed the conversations that we have here in the live stream. Now, those of you that are watching live, if you're my current student, you can interact with this live streaming session today by posting questions or comments in the Ask It channel on our Slack site. And I'm going to be monitoring that during the live stream so I can respond to those in real time. If you're watching this video after the fact via YouTube, then you'll be able to use the timestamps that are in the YouTube description that's beneath this video to jump to different points in the live stream to look at topics that you might be more interested in or less interested in. It's an hour-long live stream, so you could sit and watch the whole thing, or if you're just interested in one or two of the topics, you can jump around using the bookmarks that are beneath this video. I'll also include a few links to the other videos and resources we'll be looking at together today, so you can find those in the description down below us as well. So, it's our first meeting of the semester for pre-calculus. What are we going to be up to today? One of the unfortunate parts about pre-calculus, I think, is that really in order to really ensure that we're successful this semester, we need to make sure that all of the algebra that has come before us is working in our favor. And so the whole first 2 or 3 weeks of the course, when you take pre-calculus during a full 15-week academic semester, is devoted to this previously on mathematics kind of review, right? So we're not going to have the luxury of dwelling on that for 2 or 3 weeks. In our compressed course, we have about 2 or 3 days or so to really refresh the algebra that we're going to need to be successful. And so this is kind of the driest part of the semester, unfortunately, but hopefully it's the most familiar part of the semester for you. If you've had recent exposure to an algebra class, a college algebra, an intermediate algebra, a pre-calculus readiness, then this kind of algebra is going to be old hat, we hope. So knocking off the rust will be all that you need to do. If it's been a little bit longer, you might need to spend a little bit more time refreshing this. And in our course, I'm hoping that you're able to refresh this algebra this week so that we can move on to greener pastures. But if it takes a little bit longer, our course is sort of built this semester so that you can have the time that you need to square away all this algebra that's reviewed. So let's take a look at the agenda that I've sort of set for today. So we have kind of 2 outcomes that we want to talk about from Canvas. We're calling them A1 and A2 this semester. A1 is what I call exponent gymnastics. So how do we do algebra with exponents? And how do we keep all the different exponent properties and rules straight in our minds so that we can use them not just individually, but in concert with one another? How do we apply those exponent properties to simplify expressions involving integer exponents, so that includes positive and negative integer exponents, and then also, how do fractional exponents work? What do they do? What do they mean? How do we deal with them? So if we have a fraction, a rational number in an exponent, what does that mean? How do we handle it? That becomes a common algebra sticking point next semester when you get into calculus, because there's a lot of things that you can do in calculus with expressions only when they're written using fractional exponents. So this is one that you'll want to carry with you in particular as you go forward into calculus next semester. So we'll spend probably 30 or 40 minutes talking about exponent gymnastics. That's our first outcome for the semester. The second outcome is I want us to together kind of get an overview/review of techniques for factoring polynomial expressions. Factoring is one of those things that you spend quite a bit of time on in an introductory algebra 2 kind of setting. So I just want to give you my take on the two sort of most important factoring techniques for us. One of them being factoring out a greatest common factor monomial from an expression, and the second being able to factor a trinomial into a product of binomials using the sum and product technique. So that's kind of the 40,000-foot overview of what I'm hoping that we can do together in the next 40 or 50 minutes or so. So let's go ahead and get started with exponent gymnastics. And what I want to do is talk first about what I call the arithmetic layer cake. So what is the arithmetic layer cake, and how do I use the arithmetic layer cake to keep straight all the different properties of exponents that we care about? So this is a sort of a take that, sorry, let me fix my agenda over here. This is a take that I find to be sort of the most useful in keeping exponent properties straight, and it also kind of gives us a chance to review what the different kinds of arithmetic that we do actually mean. So let's look at the arithmetic layer cake for a minute. If we had a longer time to talk about the arithmetic layer cake, we could really sort of build up almost a historical development of how mathematics was created and how it was put on a firm, rigorous foundation. Well, we don't have time for that today. So let me suffice to say that what the arithmetic layer cake is it's a way of organizing the operations that we can do to numbers, real numbers, in a way that helps us to understand how they interact with one another. And the most basic operation that we can define is addition. The most simplest thing we can do with numbers is add them together. And as soon as we know how to add numbers together, we also pretty quickly discover that there is a way to unadd numbers together. So on each of the layers of this layer cake, there is an operation and there's its inverse. So there's addition and there's subtraction. In a way, these are the most fundamental things that we can do with numbers, and they are mirror images of one another. Whatever addition can do, subtraction can undo. So that's the first feature of this layer cake, is that there's an operation and there's an inverse. So call this the forward and the backward. Whatever addition does, subtraction can undo, and vice versa. Whatever subtraction can do, addition can undo. And that's the base layer on the cake. It's the foundation of the cake. Without that layer, the other layers of the cake, the rest of the arithmetic that we know, is sort of not possible to really make sense of. But as soon as I know how to add, there's something that happens when I add a number to itself repeatedly. Right? If I take 5 plus 5 plus 5, if I add 5 to itself 3 times, I can think of that as an addition problem, on the one hand, but I can also think of it as a different kind of problem, using a higher order of arithmetic. Because when I add 5 to itself 3 times, that is the first model for a new operation of arithmetic that we learn in elementary school called multiplication. So multiplication is, in a way, a higher order operation. It's built out of addition through the repeated addition of something with itself. Right? So if I repeat addition, that's one way of defining what it means to multiply. So multiplication is on the next layer of the layer cake. Multiplication. And of course, one of the things that you learn about these operations are what some of their properties are. So for example, adding 5 to itself 3 times can be thought of as 5 times 3. But we find out when we study the properties of these operations that we actually get the same thing when I add 5 to itself 3 times as if I add 3 to itself 5 times. They're the same answer, 15, but it's the same answer to 2 different questions. Because to add 3 to itself 5 times is to multiply 3 times 5, not 5 times 3. So even though the answers are the same, the questions are different. And the fact that multiplication works both ways is a reflection of what we call the commutative property. And so addition and multiplication are both commutative operations, right? If I have any 2 real numbers, if I add them, x plus y, or if I add them in the opposite direction, y plus x, I get different addition problems that have the same answer. Same thing with multiplication. X multiplied by y and y multiplied by x, when x and y are real numbers, are different problems that have the same answer, right? The same result. So addition and multiplication both have this property called the commutative property. Multiplication, like addition, also has an opposite. Right? It has a backwards, it has an inverse. Whatever multiplication can do, its inverse operation, called division, can undo. And that's one layer up on the arithmetic layer cake from addition and subtraction. So as we go up, the operations get more interesting, they get more complicated. They become what I call higher order operations, the higher up on the layer cake that we go. But in the same way that when I repeat addition, when I add something to itself repeatedly, we get a new operation that we call multiplication. I can do that same process with multiplication. If I multiply a number by itself repeatedly, I can create a new operation. So 3 times 3 times 3 times 3, let's say. If I multiply 3 by itself 4 times, we can check that the result of that is 81. 3 times 3 is 9, times 3 is 27, times 3 again is 81. But when I do that, I've created yet another new operation. And we call that new operation exponentiation. And I'll denote it with a little caret up here, right? Exponentiation. Running out of room there. And in that view, we write 3 multiplied by itself 4 times as 3 to the power 4. Right? And that's one layer higher on the arithmetic layer cake, because it's what we get by multiplying something by itself repeatedly, a prescribed number of times. Now, one thing that we notice about exponentiation is that exponents are not commutative. 3 to the 4th power, 3 times 3 times 3 times 3, that's 81. But if I were to reverse the roles of the 3 and the 4 here, and I would get 4 to the power 3 instead, we can check that 4 to the power 3, 4 times 4 times 4, well, 4 times 4 is 16, times 4 is 64. So clearly, 81 and 64 are not the same real number. And therefore, exponentiation does not enjoy the commutative property. Right? I can't reverse the order of what we call the base of the exponential expression and the exponent of the exponential expression. If I reverse their roles, I end up with different answers. That's not the same for multiplication. It's not the same for addition. Multiplication and addition don't care about order. Exponentiation does. So the higher up that we climb on the layer cake, the more sophisticated the operation gets, but also we lose some of the properties that we otherwise like to take for granted, like the commutative property. We even lose a property at this layer of the cake called the associative property. The associative property is the property that says if I'm performing this operation repeatedly to 3 different quantities, it doesn't matter how I group those quantities. X, y, and z, if I add them together, it doesn't matter if I add the x and the y first, and then add the z, or if I add the y and the z first, and then add the x. Those are different addition problems, but the associative property says that they have the same solution. Right? I can add the x and the y first, and then the z, or I can add the y and the z first, and then the x. I get the same answer, because addition has the associative property. The same thing is true with multiplication. If I'm multiplying x, y, and z together, all 3 of them, then even though it's a different problem, the answer, if I group the x and the y first and multiply them and then multiply by z, is the same as if I group the y and the z and then multiply by x. But the same is not true for exponentiation. Exponentiation is not associative. One way to check that would be to just think about 2 raised to the 3 raised to the 2. Okay, so let's take that exponential expression for a second, because there's 2 different ways that I could understand how to evaluate this exponential expression. And they differ based on where I place parentheses. For instance, if I group the 2 and the 3 here together first, then the first thing I would do is take 2 to the 3rd power. In other words, 8. And then I would take 8 to the 2nd power, and I would get 64. So that's what I would get if I evaluated the expression in this way. On the other hand, if I group the 3 and the 2 together first, then the first thing I would do is evaluate 3 to the second power. That's 3 times 3, that's 9. And then I would have 2 to the power 9. But 2 to the power 9 is not 64. It turns out to be 512. And so exponents not only are not a commutative operation, they're not an associative operation either. And so a lot of what makes arithmetic nice, functional, and what make it work, we start to lose as we climb higher up on the layer cake. If you're interested, you can actually keep climbing higher than exponentiation. We don't do it in any sensible introductory mathematics course. But if you're interested in what some of the higher layers on this cake are, take a look at the Wikipedia entry for what's called the up arrow notation. It's a way to make really, really big numbers really, really quickly if you're interested in it. It has a lot of really eccentric properties. So we don't study it in introductory algebra and calculus courses, but it is out there. And if you're interested, you can take a look in the links beneath on the description. I'll add a link to a great Wikipedia article about it. So even though we lose some interesting properties, one thing we don't lose is the ability to reverse an exponential operation. Whatever we can do with an exponent, we can undo. The problem is that because exponentiation is not a commutative operation, we don't just have one inverse for it, we have two. There's two different inverses for exponentiation, depending on whether we're trying to uncover the base of the exponential expression, or if we're trying to uncover the exponent of the exponential expression. And so this is a topic we're going to talk quite a bit about this semester. How do we undo an exponent? And so there's two different ways. If what we're interested in is undoing an exponent so as to discover its base, if the base is unknown, then we'll use the inverse that we call a root or a radical. And we're going to spend some time today talking about roots and radicals. It's the most elementary inverse for exponentiation. On the other hand, if what's unknown, if what we're trying to discover is the exponent, we have a different kind of inverse. And that different kind of inverse is called a logarithm. Logarithms are going to consume quite a bit of our energy later on in the semester. So those are the two different inverses for exponential expressions. Okay, so this is what I call the arithmetic layer cake. Addition and subtraction are the most fundamental level of the cake. And so they're the kind of operation that we learn first when we're learning how to do arithmetic in elementary school. Above addition and subtraction, and built out of addition and subtraction, lie the next higher operations of multiplication and division. One layer higher than multiplication and division lie the exponential expressions and their inverses, which come in two flavors, roots and logarithms. Now that we get the arithmetic layer cake, here are a couple of things we can do with the arithmetic layer cake. The first thing that I like is the arithmetic layer cake helps keep straight the distributive properties of arithmetic. The distributive properties tell us how the different operations of arithmetic and algebra interact with one another. So the distributive properties on the layer cake are one layer separated, one layer apart. So what I mean by that is that because multiplication is built out of addition, multiplication and division distribute over addition and subtraction. And so what that tells me is that, for example, an expression like 4 times the quantity 3x minus 12, right? I have a multiplication happening on the outside, I have a subtraction happening on the inside, and because those operations, layers, are touching one another, that means that I can distribute those operations. This multiplication distributes across this division. This is the foundation of how we can factor expressions as well. 4 times 3x, 4 times 12, and I can distribute. Distributing is okay because the layers are touching. On the layer cake, right? And then the same thing is also true of division over addition and subtraction. So, for example, if I have, 18x squared minus 12, and then I have divide by 3. This division distributes over the subtraction. Maybe I'll make an addition here just to switch stuff up, right? This division and that addition, the layers are touching, and so I can distribute. And I end up with 18x squared divided by 3, and I get 12 divided by 3, and the plus breaks apart. And then I can do my simplification. 18 divided by 3 makes a 6, and 12 divided by 3 makes a 4. And if that works for these layers of the cake, it also works for the top two layers of the cake. That because multiplication, for the same reason that multiplication distributes over addition, exponents and roots distribute over multiplication and division. So what does that look like? Clear out my space here a little bit. So that would look something like, if I have multiplication happening, let's say 4x, 4 times x, and then I apply an exponent to that, that exponent can distribute across the multiplication that I have in this expression. And so what I end up with is 4 gets raised to the third power, x gets raised to the third power, and the multiplication happens after that. And I can just simplify 4 to the third power. 4 times 4 is 16, times 4 again is 64, and there's my x to the third. And then the same thing is true for division as well, right? If I have 6 over y, and I want to raise this to the second power, that second power can distribute across the division as well. 6 squared over y squared, and 6 squared becomes 36. Right? So the layer cake also has this nice way of keeping the distributive properties of arithmetic straight in our mind. But the reason that we're all here is that we're also interested in how this layer cake can help us keep straight the various properties of arithmetic. So how does all of that work? How does the layer cake help us understand how to simplify an exponential expression? Let's take a look at that bit next. Oops. So to do that, let me start by taking a look at a problem, an exponential expression that we want to be able to simplify. I'm going to do that by pulling from my YouTube channel, a video from my old pre-calculus readiness course. You can find a link to this whole playlist of algebra help videos in my YouTube channel in the notes to today's video right now. So this is a problem in which we're going to be asked to simplify this expression using the properties of exponents, or what's sometimes called the exponent rules. Okay. So here's the problem itself. I'm just going to sort of write it down on my whiteboard here. And then we're going to watch this video together with a short explanation of how it works. Then we'll come back together and I'll just sort of take apart the work that happened. So here we have this expression, x to the fourth times the quantity, x to the fifth times y to the minus 2. That quantity is being raised to the third power. And then I have xy squared, which is in a big denominator. So we have a lot of arithmetic that's happening right here. A lot of algebra, a lot of simplification to do. And to simplify this, we're going to need to use probably not just one exponent rule or exponent property, but we're going to need to use several of them at a time. So let's talk together about what that might look like, and then we'll actually watch this video together. It takes about 9 minutes or so, but I think it's well worth our time. So here's my take before the video starts on how the layer cake is going to help us to do this problem. So how the layer cake is going to work is it's again going to give us a way of relating together these operations. And the way that they relate together these operations, the way the exponent rules work in the layer cake, is that any arithmetic that's happening in an exponent, so any operation that's happening to exponents, can be thought of as happening downstairs to the powers one layer lower on the layer cake. So, oh, sorry, I got that backwards. Let me erase this and fix that. Misstatement here. arithmetic that happens to exponents, arithmetic that happens to powers, and the corresponding arithmetic that happens to their exponents are one layer separated on the arithmetic layer cake. So what that means is, if I decide to multiply powers, I'll sort of annotate that on the side here. If I multiply two powers of the same base, that's the same thing as adding their exponents. Right? Multiplication of powers is the same as addition of exponents. Division of powers is the same as subtraction of exponents. And the same goes up here as well. Exponentiation of powers is the same as multiplication of their exponents. Taking a root of a power is the same as division of the exponents. So that's how the layer cake is going to help us to keep this various set of rules and exponent properties and strategies separate. Let's take a look at how this 9-minute or so video helps us to simplify the expression that we see here. Let's watch it together.
Simplifying an expression by applying the properties of exponents is a crucial algebra skill, not only because we have to do it from time to time in algebra, but more so because it really is going to test your ability to break apart an algebraic expression and systematically apply a set of rules to simplify it. In this example, we'll look at how to simplify this expression, which involves powers of x and powers of y, and all of the arithmetic operations of multiplication, division, and exponentiation. Our ultimate goal is going to be to simplify this expression so that x and y appear only in a single factor with a single exponent, and we would like for that exponent to be a positive number. So because we're simplifying an expression, as we always will when we simplify expressions, we will follow the order of operations and use the order of operations to set a priority for which parts of this expression we'd like to look at first and which parts we can leave until later. For each of the parts that we look at, our job is going to be to transform the arithmetic that's happening to the powers of x and y into arithmetic that happens instead to the exponents, the numbers themselves that are in the exponents of those powers. If we were to follow the order of operations then, the first thing that we should look at are any quantities which are in parentheses. Any quantities which are multiplied or divided inside a set of parentheses, and then that quantity raised to a power, may be simplified using the distributive property of exponents over multiplication. In other words, in this example, the quantity x to the fifth times y to the minus 2 being raised to the third power, because of the multiplication inside the parentheses and the exponent on the outside of the parentheses, that exponent may be distributed and applied to each of the factors inside the parentheses. So we can...
Let me just pause right now to just point out that this is what we were looking at in the layer cake, right? This is, in the layer cake, that's a reflection of the distributive property of this exponentiation layer over this multiplication layer. Multiplication inside the parentheses with exponentiation happening to the whole quantity afterwards. That's the same as if we distribute that exponent across multiplication. So just pointing out that that's the layer cake in action here in this example.
And turn this expression into quantity x to the fifth raised to the third power times quantity y to the minus 2 raised to the third power. This intermediate step is often skipped by many students simplifying an expression like this one, but I'm going to encourage you to leave it in to reinforce why this works and also to give us a tie-in to the next rule that we're going to look at. Now that all of our expressions with parentheses no longer have multiplication or division inside of the parentheses, we're ready to move on in PEMDAS from the P to the E and look for any expressions that involve raising an exponential expression, raising a power of x or a power of y, to another power. Here we see that there are two examples, both of which were created in our previous step. We're raising x to the fifth to the power 3, and we're also raising y to the minus 2 to the power 3. According to the exponent rules, when a power is raised to a power, we can transform that arithmetic into arithmetic in the exponents by choosing to multiply the exponents together. So in our example, x to the fifth raised to the power 3 becomes x to the power 5 times 3, or 15, and y to the power minus 2 raised to the 3 becomes y to the power negative 2 times 3, which is y to the minus 6. Having simplified all of the powers of powers in our expression, we're ready to move on from the e in PEMDAS to the m, and look for any place in which two powers of the same base are being multiplied together. So in our expression, we're going to look for any instances where a power of x is multiplied by another power of x, and or when a power of y is multiplied by another power of y. When that happens, and we can see one instance of it happening here, x to the 4th times x to the 15th, we can transform that arithmetic, multiplication of powers, instead into addition of their exponents.
So another place to point out here that we've used the layer cake shortcut now twice in this example. Once when we multiplied these two exponents together, right, the x to the 5th raised to the 3rd, that's a power of a power. So on the layer cake, that's exponentiation of a power. And according to our shortcut, that means that the exponents themselves can be multiplied. So taking a power of a power means we can multiply the exponents. So that's what we did here to get x to the power 15, and to get y to the power negative 2 times 3. That's negative 6. We then use it a second time here because I'm multiplying together two powers of x to the 4th multiplied by x to the 15th. And according to our layer cake shortcut, if I multiply powers of x, I can instead add their exponents. When the bases are the same, the bases are both x, multiplying powers is the same as adding their exponents. And so we're using the layer cake in two different ways in these shortcuts. Let's pick it up where we left off here.
So the total number of powers of x in our expression when we multiply x to the 4th by x to the 15th is x to the 4 plus 15, or x to the 19. Now there is no more multiplication of two powers having the same base inside of our expression. So we'll move on and look for any opportunities to divide. Specifically, look for where two powers of the same base are being divided one by another. In our example, there are two instances. We're dividing x to the power 19 by an x in the denominator, which has implicitly an exponent of 1 on it. We're also dividing y to the power minus 6 by y to the power 2 in the denominator. In each of those expressions, we can transform the division which is happening to the powers into instead subtraction applied to the exponents. So the total number of x's that we'll wind up with when we divide x to the 19 by x to the 1 will be x to the power 19 minus 1, or x to the 18. Likewise, when y to the minus 6 was divided by y to the 2, we can subtract those exponents and get y to the negative 6 minus 2, or y to the negative 8. Now we have achieved our first main goal.
Let's take a moment and pause and say that this answer can be thought of as completely simplified. X to the 18th times y to the minus 8. We've done all of the applications of the layer cake properties of exponent rules that we could ever need to do. But most algebra textbooks and pre-calculus textbooks are going to want us to take one more step at this point. And one of the reasons for that, well, there's a couple reasons. One of them is that if our understanding of what an exponent is to multiply something by itself repeatedly, that understanding is not sufficient for us to understand what it means to raise something to the minus 8 power. What does a negative exponent actually mean? The multiply by itself idea doesn't work, because how do you multiply something by itself a -8 number of times? That just doesn't make any sense. And so this last step conceptually helps us to understand what that exponent actually means, because what we're going to do is rewrite this expression so that its exponents are all non-negative. We don't want any negative exponents in our answer, just for the sake of our own understanding. The second reason is a more instrumental reason. When you go on to calculus, there's a lot of techniques in calculus that are going to require you to interchange negative exponents for different kinds of arithmetic. And when you spot certain kinds of arithmetic in calculus, you're not going to be able to do calculus with those expressions unless you translate that arithmetic into negative exponent arithmetic. So this translation back and forth from negative exponents to non-negative exponents is an important strategic technique for calculus next semester as well. So let's jump back into the explanation of what's going to happen next here with this expression. It's really the last step in the simplification
problem, which is to make it so that there is only one factor having each of our variable bases in it. We have only one power of x and only one power of y left in our expression. So the last thing to do is to transform this expression one last time in a way that takes any exponents which are negative numbers and trades them instead for exponents which are positive. In our example, the power of y to the -8, has a negative number in its exponent. We can turn any negative exponent positive by trading out multiplication of that power by division by that power. So to make a negative exponent positive, what we can do is move that factor, y to the -8, from the numerator of the fraction in which it resides to the denominator of the fraction in which it resides. Or, if the negative exponent were already in the denominator, we would do the opposite, move it from the denominator to the numerator. So when a power is moved from numerator to denominator or vice versa, the exponent will switch from negative to positive or vice versa. Here, because we haven't written this expression as a fraction, we can imagine that there is an invisible denominator of 1, and moving y to the -8 down into that denominator turns its exponent into positive 8 instead, and gives us our final expression, which we will use as our answer, x to the 18 over y to the 8.
And so that's our complete explanation of how to handle using the various exponent properties in concert with one another. And you'll notice that in this video I've kind of used PEMDAS, the traditional description of the order of operations, both as a way to understand how the layer cake fits together, but also as a way to organize your strategy in simplifying these expressions. So the first thing that I did was I looked for parentheses. I looked for opportunities to distribute exponents across multiplication or across division. And in the very first step of this problem, we did distribute the exponent of 3 across the multiplication inside the parentheses, grouping this x to the 5th multiplied by y to the -2 together. So first look for those distributive property opportunities. And then once you've distributed, then we started working our way through the order of operations looking for e, exponents, powers of powers. And we had powers of powers sitting right here, x to the 5th raised to the 3rd, y to the -2nd raised to the 3rd. We can simplify a power of a power, again, remember the layer cake, by going one step down on the layer cake. A power of a power means multiply the exponents. And when we multiply the exponents, we ended up here at this step, x to the 15th, y to the -6. And then I have a product of powers to worry about, multiplication. Two powers of the same base multiplied together. And when that happens, again, following the layer cake, if I'm multiplying two powers of the same base, I need to be adding their exponents. And that's exactly what we did here, adding the 4 and the 15 to get 19 as my exponent on x. And then because it works for addition of exponents and multiplication of powers, it also works for division of powers and subtraction of their exponents. Again, for the same reason. The layer cake is helping me to keep that arithmetic straight. And so we used that division to subtraction property to reduce the number of x's from 19 to 19 minus 1, and the number of y's from -6 to -6 minus 2. And then we had only a single factor in which each of our bases appears. We only have one place where we have powers of x, only one place where we have powers of y, and so we're completely simplified, except if we want to make all of our exponents non-negative, which we usually do for a variety of reasons. And any negative exponent in your final answer can be transformed into a positive one or a non-negative one instead, just by moving it from numerator to denominator or vice versa. In this example, that meant moving the y to the minus 8 into a denominator to become y to the positive 8. So if you can navigate these kinds of problems, your problem-solving muscles are really being developed in a problem like this, because you have a variety of different rules. When do I apply them? How do I apply them? When are they appropriate? And so this is a really good sort of prototype problem for our first learning objective, learning outcome for this semester of pre-calculus. The next step in our journey that I want to take is to talk about one of the pieces that didn't really get mentioned in this first example. And that is, what about exponents that are fractions? How do we handle fractional exponents? What does it mean to raise a quantity to a fractional power? And really the answer to that is, again, no surprise, found in the layer cake. So what I want to do is just take a moment and let's evaluate just an arithmetic problem. So the question I'm going to pose here is, what does it mean to take the number, let's say we take the number 81, and I want to raise that number to the power negative 1/2. Or no, forget it. Let's raise it to negative 1/4. So we know what these numbers are. We know what the number 81 is. We can conjure up a mental picture of what 81 means, right? Maybe take 9 things and 9 things and make a 9 by 9 square, and that 9 by 9 square is an area of 81. However you like to think about what the number 81 is. We also kind of have an understanding of what 1/4 means, right? It's the relationship that the number 1 has to the number 4, which is the same as the relationship that the number 4 has to the number 16, or the number 10 to the number 40, and so on, right? We know what 1/4 is. We also kind of know what it means to take a negative of 1/4 and just move to the other side of the number line. But what does it mean when I put all of those numbers together in an exponential expression? What would it possibly mean to raise the number 81 to the negative 1/4 power? How can I multiply a number by itself negative 1/4 number of times? Well, the first thing that we might recognize is that we just previously answered the question about negative exponents. We kind of understand that raising a base to a negative exponent trades out multiplication for division. It trades out numerators for denominators. So instead of thinking of the negative 1/4 power of something, we now know that we have tools for trading a negative exponent out for a positive one by reversing the role of multiplication and division. In other words, reversing the role of numerator and denominator. So the first thing that I might do is I might just turn that negative exponent positive. I can make it 81 to the power positive 1/4 if I put that expression in the denominator instead of in the numerator. And because I'm leaving my numerator empty when I do that, I'm moving this whole thing downstairs, that means that I need a 1 to denote the empty numerator left upstairs. So at least we've handled the negative exponent problem. We know what to do with that. So what about the fractional exponent problem? What in the world is 81 to the power 1/4 supposed to mean? So let's just make some new space here, and let's try to talk this through systematically. 81 to the power 1/4. What is this thing supposed to mean? Well, anytime we don't know what something is, we have the luxury, if we want to, of representing that unknown quantity by a variable. Let's call that variable x. So x is this thing that we want to understand. So what is x? What is the value of x? What does it mean? And so now I kind of have this algebra problem that I can use the tools of algebra to help me solve. And so one of the ways I can do that is I can use my arithmetic layer cake. And I'll use my arithmetic layer cake to try and turn this exponent of 1/4 into a whole number instead. Because we know what raising something to a whole number power, a whole number exponent is supposed to mean. Multiply that quantity by itself a certain number of times, right? So I want to turn this 1/4 into a whole number. And the best way that I know of to turn a fraction into a whole number is to somehow multiply that fraction by its own denominator. 1/4 times 4. 1/4 multiplied by 4 is just equal to 1, right? After all, 4 is the same as 4 over 1, and when I multiply fractions, I multiply them straight across. So 1/4 times 4 is the same as 4 divided by 4, which is equal to 1. So if I can somehow multiply this exponent by 4, then on the left side of my equation here, I'm going to get 81 raised to the power 1. And to raise something to the power 1 is the same thing as just to understand that number itself. Raising something to the 1 power is just equal to the base itself. But the question is, how do I, if I multiply this exponent by 4, what am I really doing to this expression? How do I multiply an expression in its exponent? Well, we know that answer from the layer cake. If I want to multiply the exponents in an expression, what I ought to do to that expression is I ought to exponentiate it. I ought to raise it to a power. So there's the layer cake in action again. So to multiply this exponent by 4, what I'm really doing according to the layer cake is I'm really raising this whole expression, 81 to the 1/4, I'm raising that expression to the 4th power. And if I do that on the left side of my equation, I also need to do it to the right side of my equation in order to keep my equation balanced. Remember, that's the main principle of solving an equation or manipulating an equation in algebra, is whatever we do to one side of the equation, we have to do the same thing to the other side. Otherwise, we've completely lost the meaning of the balance that that equal sign brings to the table. So when I multiply my exponent on the left side by 4, what I've really done is raise that side of the equation to the 4th power, which means I have to raise the right side of the equation to the 4th power as well, and I get a new equation. 81 equals x to the power 4. And so what this does is it gives me a new way of understanding what x is. And that way is x is something which, when I multiply it by itself 4 times, x times x times x times x. That's, after all, what x to the 4th power means. It's something which, when I multiply it by itself 4 times, I get 81. Right? Well, okay. Now we kind of understand that what we're doing is we're talking about a solution to what's often called a root problem. In other words, x is what we call the 4th root of the number 81. That's just a definition. That's just what it means to be a root in the first place, right? It's the 4th root of 81. And very often, we use a special kind of notation to express roots, right? We take the number 81 and we place it underneath one of these weird crookedy symbols that we call a radical sign. And then in the little crook of this radical, we place what's called the index of the radical. How many times do I have to multiply by x by itself to get 81? 4 times. So I'll put a little tiny 4 in the crook of that radical. So the 4th root of 81 is the meaning of x. It's the 4th root of 81. That doesn't really tell us how to calculate x, but it does give us a convenient compact notation to represent what these kinds of quantities are. 4th root of 81. And so if I want to know what the 4th root of 81 is, I just ask myself, what do I have to multiply by itself 4 times in order to get 81? Maybe 2? Well, 2 times 2 times 2 times 2 is 16, so that's too small. What about 5? 5 times 5 times 5 times 5, 625. That's too big, so something between 2 and 5 maybe. What about 4? 4 times 4 times 4 times 4, 256. Now that's too big. 3 times 3 is 9, times 3 is 27, times 3 is 81. Oh, we figured it out, right? And so the 4th root of 81 is otherwise known as 3. But we got into this conversation because what we were interested in is understanding what fractional exponents mean. And according to this whole conversation, what I hope that we've sort of landed on here is that any time we have a fraction in an exponent, it really means that we're taking a root. And the index of that root, the thing that goes in the crook of my radical, ends up agreeing with the denominator of the fraction that I had in my exponent. So let's see if we can use the arithmetic layer cake to bring some sanity to this part of the conversation. So 81 to the minus 1/4, just to finish this problem. We now know that 81 to the 1/4 power is the fourth root of 81, which is otherwise known as 3. And therefore, 81 to the minus 1/4 ends up being 1/3. So there's the end of that problem. And so if we want a hard and fast rule for what do I do when there is a fraction in my exponent, inspired by this example, I think we can see what to do now. That anytime I have a quantity, and I'm going to use a variable here to represent this quantity, let's just call it x. Again, every mathematician's favorite variable. If I have a fractional exponent on my x, that fraction is going to have a numerator, and it's going to have a denominator. Let's call the numerator p, let's call the denominator q. And so I have a fraction up here, p divided by q. What do I do with the p? What do I do with the q? Well, in the example that we just did, we saw that the denominator ends up giving us the answer to what is the index of the radical that we're really taking. Which root are we really talking about? The denominator was 4, so we were talking about the fourth root. And so the principle here is we'll just take that denominator and we'll make it the index of my radical. So any denominator that you see, just make it a radical sign with that denominator as the index of the radical. And then my x ends up being the star of the show underneath my radical. Well, okay, but then what about my numerator? What do I do with this p? Let's go back to our last example and soup it up a little bit to try to get an answer to that question. What if instead of asking you for 81 to the 1/4, what if I'd asked you for 81 to the 3/4? So let me stick a 3 in here. We'll see how that changes our game. Well, we can look at it in a couple of different ways. It's still true that when I take 3/4 and I multiply it by 4, I get a whole number exponent. And that's good news because we know how to raise numbers to whole powers, right? So when I do 3/4 times 4, I'm going to get 81 to the power 3. And so one way of approaching this problem, and it's one way that we can sort of go back here and make sense of what's happening, we can take this numerator and make it the power of x underneath that radical over there. So it's a qth root of x to the power p. That's one way of looking at this expression. And taking that approach, the first thing I would do here is I would want to know what is 81 to the power 3. And that's probably a big number. So I take out a calculator and I do 81 times 81 times 81. I get this gigantic number. Where's my camera? 531,441. So that's one way of doing this. It may not be the most efficient way, but it's certainly correct. One of the habits that I hope to break you of this semester is thinking that there's only one way to do an algebra problem. There are ways that preserve correctness and soundness and validity of our logic, and there are ways that don't. But within that category of ways that preserve soundness and validity of logic, there can be many different ways, each of which is equally correct, but some ways might be more efficient than others. I would categorize this way as not particularly efficient, because now we have a gigantic number, 531,441, and I want to know what's the fourth root of that. And I'm not particularly inclined to do the rest of the problem this way, but this is certainly from the point of view of algebra. Algebra doesn't care, right? We could put that big power, x to the p, underneath my qth root, and that's totally fine. It's valid, it's correct algebra. But the good news is, there's another way. Rather than taking the third power first, what I could have done instead is I could have traded places. So what do I mean by that? I could choose to pause here. And instead of computing the third power of 81, as we did right here, maybe what I want to do next, maybe instead of thinking of this as 81 to the power 3/4 and doing the fourth root, doing the third power first and then worrying about the radical, what if I did the radical first and then I worried about the third power afterwards? After all, this is the other great thing about fractions. 81 to the power 3/4, let me clear out some space up here so I can write what I'm about to say. 81 to the 3/4 is the same as 81 to the 1/4 raised to the power 3. So I could take the radical first and then take the power, instead of, as we're trying to do here, take the power first and then take the radical. Those operations can be reversed, because multiplication is commutative. 1/4 times 3 is the same as 3 times 1/4. So it's a more efficient way, probably, to figure out what is the 1/4 power, and then take that and raise it to the third. So in that viewpoint, instead of putting this pth power under the radical, I could instead put that pth power outside the radical. So maybe put some parentheses here, and then put the p on the outside. And that is also equally valid. And the reason that that's nice is that we already know what 81 to the 1/4 power is. 81 to the 1/4 power is the 4th root of 81. We figured out that that was 3. And so this 3 on the inside, we can then raise to the 3rd power. And that is a much simpler thing to do. That's 3 times 3 times 3. That's 27. And so rather than taking the 4th root of a gigantic number, we're just taking the 3rd power of a smaller number. 3 times 3 times 3, 27. And so computing an expression with a rational exponent, we have two different ways of approaching it. And each way involves us taking a power and also taking a root. But we can do those two in either order that makes sense, either order that makes this a tractable problem for us. And personally, I think the easiest way is to take the radical first, the qth root of x, and then take that result and raise it to the pth power. For me, that's the quickest way to do a fractional exponent. So that's going to be where we sort of pause and sort of conclude our exponent gymnastics portion of our live stream for today. I do want to take another 20 minutes. We're going to run a little bit over time here, but that's okay, because you can always catch up on this later and watch it on our YouTube channel. And I want to go forward and look together at a couple of factoring techniques to kind of give a preview of the next topic that's coming. We'll talk a little bit more in factoring in detail in our next live stream later on this week. So as you run across tricky factoring problems, please do make a note of them, dog-ear them, contribute them if you're my current student into our Slack Ask It channel, so that I can make sure to address them in our next live stream. But I want to wrap up today's live stream by giving a preview of those factoring techniques. So where are we going to go next with our overview of factoring? So what is factoring? Factoring is nothing more than a way of, again, rewriting an algebraic expression in an equivalent fashion. But what factoring really is it's a way of undoing the distributive property of mostly of multiplication over addition. It's interesting to think about whether we could use a similar approach to rewrite exponential expressions from up here. But if we want to rewrite an expression that uses multiplication and addition, what are some ways of doing that? So as with our last example, what I want to do is I want to start with, well, let's start with an example that is sort of more complex. And then we're going to kind of try to break it down into a couple of smaller pieces for today's live stream. And then hopefully talk about those pieces individually and then worry about them in concert afterwards. So here's the problem that I want to tackle. This is, again, one of the videos from my algebra playlist, if you want to take a look at it later. So I give you an algebraic expression here, 9x to the 5th plus 24x to the 4th plus 12x to the 3rd. This is an expression called a polynomial. Poly because it has several terms added together, a 9x to the 5th, a 24x to the 4th, a 12x to the 3rd. Nomial because each one of those terms is made up of multiplication of a power of a variable and a constant coefficient. 9 times the 5th power of x, 24 times the 4th power of x, 12 times the 3rd power of x. So what I want to do first, before we jump into actually solving this problem and trying to factor this expression completely, is I want to give us a frame a conceptual scaffold for understanding what factoring is and the ways in which it is nothing more than a reversal of the distributive property of multiplication over addition. So let's take a look at this expression really quickly. I like here to borrow from a set of strategies that's sometimes called, quote-unquote, the new math. And it's often called the new math in a joking, sort of derisive way. But I really think there's a lot of value to understanding what we're about to do in sort of the new math way of doing it. Because what I have here is an expression that adds together three terms. And what I'm going to do is I'm going to take those terms and I'm going to put them into their own separate little containers here. So I have a 9x to the fifth, and then in a separate container I have 24x to the fourth, and then in a separate container I have 12x to the third. I'm separating them from one another because they're not what we call like terms. They're not like terms because their variable factors, x to the fifth, x to the fourth, x to the third, are not identical. They're not the same powers of the same base. Right? The bases are all the same, but the powers are all different, 5, 4, and 3. So we're going to separate them apart because they're not like terms. Now, factoring is asking the question, what can be multiplied together to give me those terms? What do these terms have in common? So that's the first question I like to ask myself. What is in common to all three terms? And the answer to this question should help us to get started. If I look across all three of these terms, the first thing I notice is that they all have a factor of x in common. So one way of starting this process might be to say, well, why don't I take and observe that all three of my terms have an x in common? That's going to begin my factoring process. And the role that that x there is going to play is it's going to become a part of one of the factors in my answer. So I'm going to have, I'm going to have an x in my answer. And then attached to that x is going to be some quantity of stuff, right? Which, if I were to distribute this multiplication by x across the terms inside of these parentheses, I should get my original expression back. And the question is, if x is in common to all three of these terms, what distinguishes them? What do I multiply x by in order to get 9x to the fifth, for example? So this is how this little method works. X multiplied by what is going to give me 9x to the fifth? And the observation, of course, is that if I multiply x by something to get 9x to the fifth, that something is going to be the missing factor in the problem, x times what equals 9x to the fifth. It's the solution to a division problem. 9x to the fifth divided by x. That's what the factor that belongs here is going to be known as. But we know already how to simplify that expression from the distributive property of exponents over division, because their layers are touching in the layer cake. I can take these powers of x, x to the fifth, x to the first, and I can simplify their quotient by subtracting their exponents. X to the fifth divided by x to the 1 is x to the 5 minus 1, or x to the 4. And so my missing factor here has 4 powers of x in it. And it has a 9, of course. And so then that 9x to the fourth becomes the first of my terms in the factor that's multiplying by x right here. So x times 9x to the fourth gives me 9x to the fifth. That same logic will tell me that the missing factor here is 24x to the power 3. And I'll put a plus sign in front of it here to remind myself that that's what's happening. 4x to the 3. And similarly over here, 12x to the 2. And I have factored this expression. 12x to the 2. And we can check, again, using the properties of exponents, that if I were to multiply this expression back out using the distributive property of multiplication across addition, I would get x times 9x to the fourth is 9x to the 4, x to the 1. Adding those exponents, 4 plus 1, gives me the exponent of 5, and it gives me this expression back. Ditto with this one, ditto with that one. So we've factored this expression, but we haven't factored it completely, because we haven't found the best answer to the question right here. What do all three of these terms have in common? They certainly all have an x in common, but when I look at these three purple things right here, these terms still have something in common. They have more x's that I could have factored out. And so we haven't really factored this expression completely until we've taken out as much as we can, identified all that these terms have in common. So they don't just have one x in common. If I look in these terms, they actually have 3 powers of x in common. There's 3 x's in here, there's 3 x's and more so in here, and there's 3 x's and then some in here as well. So if I wanted to factor this expression completely, I would want to observe that there's in fact an x to the third power that's in common to all 3 of these terms. And that's then going to revise my cofactor, right? The terms that I have written up here in purple. Because now the missing factor between x to the third power and 9x to the fifth power is going to be the 2 missing powers of x, so that x to the third times x to the second is going to give me x to the 3 plus 2, or x to the fifth. So now this missing factor is x to the power 2, and we'll revise the factor up here as well. Ditto for this one. The missing factor between x to the third and x to the fourth is x to the power 4 minus 3, or x to the power 1. So we'll revise this one. And then the missing factor between x to the third and x to the third is x to the power 0. X to the power 0 is a missing x factor. It's equal to just the number 1. And so we'll get rid of that. And now we have an even simpler way of understanding what cofactor that I can put here, right? Because now these 3 terms in my purple cofactor don't have any power of x in common to all 3 of them. Because after all, this term on the end has no x's to give left. But we're still probably not done, because these 3 terms might have a constant, a number, that they share in common. 9, 24, and 12 all have a common numerical factor that they can all be divided by, namely 3. All 3 of those numbers, 9, 24, and 12, are divisible by 3. And so I don't just have to take out an x to the third. I can also put on my arithmetic hat and take out a numerical factor of 3. That then becomes a part of my coefficient out here in the front. And again, I have to revise my cofactors. What's the missing factor between 3 and 9? That missing factor is 9 divided by 3, otherwise known as 3. So I'll revise this cofactor here to be 3x squared. Similarly, the missing factor between 3 and 24 is 8. So I'll make this an 8. And the missing factor between 3 and 12 is 4. So I'll make this into a 4. Now, let's ask the question again. Is there anything in common to these 3 terms in my cofactor, 3x squared, 8x, and 4? Well, they don't have x's in common, because this one on the end has no x's to give. And 3, 8, and 4, the constants, also don't have anything in common. There's no number that is a divisor of 3, 8, and 4, except for the most boring answer, which is 1. 1 is a factor of everything, so it's not that interesting. And so now we have completely factored out as much as we can that was in common to all 3 of these terms. And this, 3x cubed, is known as the greatest common factor of these expressions. And so looking for the greatest common factor of all 3 of the terms in an expression is what I always recommend to be the first step. It's only after we think about the greatest common factor, which in these expressions is always going to be a monomial, that taking out the greatest common factor is the first thing that we want to do. And only after we've done that, then we'll worry about what comes afterwards. So I've kind of just walked us through what this next video is about to say. So maybe we'll just watch this next video in double speed. So this will take 4 minutes, and it's going to sound a bit like a chipmunk talking. But let's take a look at this factoring out a monomial using the greatest common factor method together. And then we'll go forward to the next technique, which is what do we do about binomials? How do we use the sum and product technique to keep going in a problem like this where we've left off? So let's take a look at what happens next.
In algebra, factoring an expression means breaking it apart into 2 or more expressions which are multiplied together, and that product is equivalent to the original expression. There's a wide variety of methods to factor an expression in algebra, ranging from the simple to the quite intricate. And even worse, factoring an expression is not even always possible the way that we want it to be. But let's start out with the simplest method of factoring an expression possible, which is to, among an expression with multiple terms, factor out a monomial, a single-term expression. To factor a monomial expression out of a polynomial, such as the one we've written here, let's first remind ourselves that to factor means to break the expression apart into 1 or more pieces which are multiplied together. So I'm going to write a blank shell of one expression multiplied by another expression in parentheses that we're going to try to fill in a way which, if we were to re-multiply that expression back out, we would arrive back at the original expression we started with. So how can we factor a monomial out of the polynomial expression 6x to the fourth minus 9x squared plus 15x? First, we want to identify the greatest common factor of the three terms that make up this expression, 6x to the fourth, 9x to the power 2, and 15x. In order to find the greatest common factor of these terms, we're going to look for the largest expression, in a certain sense, which each of these terms is divisible by. We'll do that first by focusing on their coefficients. In this example, the coefficients are 6, 9, and 15. And we'll find the greatest common factor of that triplet of numbers by discovering their prime factorization, and noticing that each of their prime factorizations has a 3 in it, and that is the most that these three numbers share in common. So the greatest common factor of 6, 9, and 15 is the number 3. That number will then be the coefficient of the greatest common factor of these.
So I just want to pause right here to note that this is a little bit more systematic way of understanding how to determine the greatest common factor of monomials. So I think there's some value in looking at this presentation as well. The best, most efficient way of finding the greatest common factor of numbers is to understand their prime factorizations. Break 6, 9, and 15 apart completely and figure out what they all have in common. In this case, the only thing that they all shared was a single power of 3. But if they shared multiple things, we would multiply those things together to determine the greatest common factor. Now let's pick up where we left off.
Three terms. But we're not done yet finding the greatest common factor, because in addition to having a coefficient, each of our original terms also had a variable factor to deal with, which was a power of the variable x. Fortunately, finding the greatest common factor from among those variable factors has a simple shortcut. We need only to choose the lowest exponent that we can find. Since the exponents on our powers of x are 4, 2, and 1 in our three terms, we will choose the factor with the lowest exponent, x to the power 1, to be the variable factor of our greatest common factor.
So there again is another way of looking at the problem that we just did sort of ad hoc a minute ago. The shortcut, the mental shortcut, and these shortcuts are valuable, particularly the more that we go into pre-calculus and calculus, and you don't want to have to think as much about the algebra as you're doing it. The shortcut for the greatest common factor of monomials is for each of those variables, choose the lowest exponent that's present. So in this case, the exponents on the x's were 4, 2, and 1, so the greatest common factor had an exponent of 1.
So at the end of this process so far, we've discovered that the greatest common factor of the three terms 6x to the fourth, 9x to the second, and 15x to the first is an expression whose coefficient is 3, which is the GCF of 6, 9, and 15, and whose variable factor is x to the power 1, because that was the lowest exponent on the powers of x in our terms. Great, so I think that was the trickiest part of this problem, but we're also not done just having identified the greatest common factor, because the task in factoring is not just to discover what may be factored out, in this example 3x, but also what that factor must be multiplied by to recover our original expression back again. So what's missing is the quantity in this other set of parentheses that I like to call the leftovers. When 3x is factored out of 6x to the fourth minus 9x squared plus 15x, what remains in that expression? We can find that, most simply I think, by dividing the expressions by one another, dividing them by the GCF. So if I divide 6x to the fourth, 9x to the second, and 15x to the first by 3x to the first, I will discover what belongs in the leftovers. And when we divide a pair of monomials, the coefficients, the numbers, divide. Therefore, the coefficients in my leftovers are going to be the results of dividing 6, 9, and 15 by 3, the coefficient of our greatest common factor. Simplifying those coefficients, we end up with a 2, a 3, and a 5. So those are the coefficients in my leftovers. How about the variable factors? The variable factors we will discover by dividing the powers of x in our terms by the power of x in our greatest common factor. So here, we're dividing two exponential expressions with the same base. And when powers divide, their exponents subtract. So if I were to divide x to the fourth by x to the first, I would get x to the power 4 minus 1, or x to the 3. Likewise, dividing x to the power 2 by x to the power 1 gives me x to the 2 minus 1, or x to the 1. And dividing x to the 1 by x to the 1 gives me x to the 1 minus 1, which is x to the power 0. And because any variable raised to a 0 power is interpreted as the constant 1, in other words, that x to the 0 becomes a factor of 1, which is an invisible factor, making our power of x disappear. So the leftovers, in the factor on the right, have as their terms 2x to the third, 3x to the first, and the constant 5. To finish, we just need to restore the signs that connect those three terms together from our original expression, a minus in front of the first pair and a plus in front of the second pair. We can also clean up our answer by not writing the power of 1 on our exponents of x, giving us the final factored expression, 3x times the quantity 2x to the third minus 3x plus 5.
And that will wrap up our greatest common factor approach. And as I said, this is always the first technique that I think about when I think about factoring a polynomial in general. It's kind of the low-hanging fruit. And it's the simplest method. It's also the one that I think tends to get forgotten. And if you forget it, it can turn a sort of medium difficulty factoring problem into a really difficult factoring problem. So definitely don't skip over this greatest common factor technique. So the last technique that I want to look at together for factoring is probably the one that people remember the most. And that is, how do I factor a trinomial expression? How do I factor a quadratic? And I'm just going to let this example kind of do the talking for me here. I want to factor the quadratic expression 5x squared minus 10x minus 40. And as in our previous examples, the first thing that's going to happen in this problem is we're going to look for the greatest common factor and pull out that greatest common factor right away at the beginning. But before we launch into this example, let me just give you a quick reminder of why. So why do we care? Why do we want to be able to factor expressions? It's not just a medieval torture device for students taking algebra and pre-calculus courses. Its purpose is actually to help us to solve equations. After all, that tends to be one of the main things that we like to do in algebra class. So how does factoring help us to solve an equation? Just get a quick reminder of that before we move forward with the actual method, the strategy for this kind of factoring. So how does factoring avail us? What does it do? So if I could somehow figure out how to factor this expression, I would be able to solve this equation for x. I would be able to determine what values of x make 5x squared minus 10x minus 40 equal to 0. And the reason that that's possible is if I'm able to factor this into two expressions, whatever those expressions are, let's call them the purple factor and the green factor, then I would be able to rewrite this equation as something times something equals 0. And the greatest thing about 0, it's got a lot of great things about it, but the greatest thing about 0 for most students in algebra is that the only way to get 0 as the answer to a multiplication problem is to have one of our factors in that product having been 0 in the first place. It's not possible to multiply two non-zero numbers and get 0 as our answer when those are real numbers. And so in algebra, this becomes what we call the zero factor property. The zero factor property tells me that when a product of two expressions is equal to 0, then necessarily one of those expressions, or possibly both, must have been 0 to begin with. So what it does is it takes one complicated equation and it breaks it apart into two simpler equations. Right? And this is the step that people forget. You go through all the difficulty of actually factoring a polynomial expression, and then a lot of students get to this step and they're like, okay, now what? What do I do? And they forget that a product of two expressions cannot be 0 unless one of those expressions was 0 to begin with. And these expressions, these little ones, are always simpler to deal with than the original one that we started with. So this is the moral of the story. This is why we care about factoring, is it gives us tools to solve equations that we weren't previously able to solve. And with that lens on this problem, let's take a look at the strategy. How do I factor a quadratic trinomial? This video is about 10 minutes. It's going to be the last thing that we do together in today's live stream.
While factoring out a monomial from a polynomial may be the simplest factoring technique in all of algebra, perhaps the most broadly used factoring technique in algebra is that which permits you to factor a quadratic trinomial. So that's a polynomial whose highest exponent is 2 and which has 3 terms, such as the one we're looking at right here, into a product of a binomial times another binomial. In other words, to write this as a product of one polynomial with 2 terms times another polynomial with 2 terms. One of the reasons this is such a beneficial thing to do is something you'll appreciate in the next video, because to factor a quadratic trinomial gives us a way to solve an equation that has a quadratic trinomial in it for its variable. After all, that's the ultimate goal of learning how to factor, is it gives us perhaps the most powerful tool for solving an equation that involves a polynomial, because reversing the order of operations is not sufficient in general to solve a polynomial equation. So how can we factor this quadratic trinomial into a product of one binomial times another binomial? First, and this is going to be true in general of any expression we wish to factor, let's try and do the simplest factoring that we can do first, and look and see if when we break this apart into a product of one expression by another expression, whether there's an opportunity to first factor out the greatest common factor of these 3 terms. In this example, That answer is yes. Finding the greatest common factor of 5x squared, 10x, and 40. We first find the greatest common factor of the coefficients 5, 10, and 40, which is 5, and then multiply that coefficient by the smallest power of x that we see. And since the term with the smallest power of x is this term, which has no power of x in it at all, no power of x survives into our greatest common factor. But we do find that the three terms which make up our original polynomial have a 5 in common, and we should begin the process by factoring out that greatest common factor. So we'll first bring a 5 outside, and inside determine the leftovers by dividing each of the three original terms by 5. Dividing 5x squared by 5 gives me just x squared. Dividing 10x by 5 gives me 2x. And dividing 40 by 5 gives me 8. So we've first succeeded in factoring out the greatest common factor of these three terms. The expression that we're left with, x squared minus 2x minus 8, is still a quadratic trinomial. Quadratic because the largest exponent is 2, and a trinomial because it involves three separate terms which cannot be combined together because they're not like terms to one another. So we're going to need a new method if we want to factor that part of our expression, x squared minus 2x minus 8. The method that we're about to use works only when the coefficient of our highest order term, the x squared, is 1, which it is in this example. When that coefficient is 1, we can use a technique called the sum and product method to determine how to factor this quadratic into a product of one binomial times another binomial. The sum and product method works by searching for a pair of integers, whole numbers, whether they're positive or negative, that has two properties. The first property is that the product of these two numbers has to give us the constant term of our quadratic trinomial. So our numbers have to multiply together in this example to give minus 8. But that same pair of numbers must also add together to give us the coefficient of the term which has x to the power 1 in our quadratic trinomial. So in this example, that same pair of numbers which we choose that multiplies together to give us negative 8 must also add together to give us negative 2. Typically, solving this sum and product question begins by thinking up pairs of whole numbers which multiply together to give the desired product. For negative 8, I might think of pairs like negative 8 times 1, negative 4 times 2, negative 2 times 4, or negative 1 times 8. Of those pairs, the pair which also adds together to give us negative 2 is the pair negative 4 and positive 2. We can check that when those two numbers are multiplied together, their product is positive 8. And when that same pair of numbers is added together, their sum is negative 2. So this is the pair that we're looking for. What do we do with those numbers? Well, those numbers become the constant terms in our pair of binomials, which will multiply together to give us our trinomial. So minus 4 and plus 2 become the second terms in our binomials, of which the first term will be x. And our complete factorization of this polynomial, therefore, includes the product of x minus 4 with x minus 2. This product gives us this quadratic trinomial back, x squared minus 2x minus 8. But don't forget that it also must include the greatest common factor that we factored out in the beginning, which is our
So hopefully this is ringing some bells for people. One of the most important things that we end up doing with this is and we're going to talk quite a bit about this in our next live stream later on in the week, is that these are also key tools, not just for solving equations, but also for simplifying rational expressions. So algebraic expressions that have polynomials divided by polynomials. We're going to do quite a bit of studying those kinds of functions. So functions that are polynomial or rational in type later on in sort of the third of our 4 acts in our course, the third of our 4th chapters that we look at later on. And so those strategies end up getting used there a lot as well. So hopefully today's session has helped bring back some algebra for you. It may have raised more questions than answers, and if it has, and if you're my current student, please don't be shy to ask those questions in our Slack channels. Join the conversation, be working on those quizzes, communicate with your members of your group, your other classmates, communicate with me. I'm happy to help out with what you need. This beginning of the course is kind of... there's no way of getting around it. It's kind of intense for the first few days just because there is so much algebra that we're trying to look back on at the same time. But what I'm hoping is that by the end of this review, you've knocked enough of the rust off for us to begin to start making some progress toward thinking in new and different ways. Because pre-calculus is not ultimately about all of this algebra. This algebra is here as a tool for us to be able to solve problems, but it is not the point of pre-calculus. The point of pre-calculus, as we're going to see as we transition out of this topic into the next one, is to be able to use mathematical objects called functions to engage in processes of modeling, so understanding phenomena in the real world around us, or in the sciences, or the physical sciences, the social sciences, how to model those phenomena and understand the ways in which they model processes of change. How do we use functions to model changing processes? That really gets amped up in calculus. So pre-calculus is laying the foundation for that. And algebra is it's the screwdrivers, it's the hammers, it's the bandsaws, it's the things that we need to use in order to build this structure of functions modeling change that we ultimately want to get to. And so the algebra is important, it's essential, we need to have it working for us so that we can do the work. But algebra is not ultimately the point of what we're doing together this semester. And that should be good news, because by now that you've already made it all the way to pre-calculus, you've got a lot of algebra under your belt, and you've been hit over the head with properties and rules and solving equations and simplifying expressions over and over and over again. You're probably ready for some fresh thinking and some big ideas and concepts. And that's what I'm hoping pre-calculus will help you to get. And just in the first few days of this course, we're going back and looking over that algebra again, just to make sure that it's there for you when you need it. So I look forward to working with you this semester. Please leave comments and questions if you're my student in our Slack channel. If you're not, feel free to drop them in the comments box underneath here on YouTube. And I look forward to having more of these live streams with you over the course of the semester as we go through pre-calculus together. I'll see you the next time.